Well, now we have one example for manipulating the equations that we have seen so far. So, example number 11.4. Okay. It is saying it is required to define the electromagnetic field equations for low frequencies in a highly conductive material in terms of the magnetic vector potential A. So highly conductive material, it means that conductivity of a material is much higher than much higher than 1. So, and the material may be assumed to be linear, homogeneous, and isotropic in all its material properties. Show that by using Coulomb's gauge, or is this is called the Coulomb's gauge, the field equations can be reduced to up to this point. So, first of all, let's write the field equation. So it was defined. Okay, here let's write this equation. Gradient of divergent of A minus the Laplacian of A equals to mu J minus mu epsilon, so d squared A over dt minus the gradient of mu epsilon of dv over dt. So in order to simplify this equation, we have to find a way of eliminating the first term on the left hand side, or in other words, we are given Coulomb's gauge, which says that divergence of magnetic vector potential is 0, so it means that this term eliminates, and remains that minus Laplacian of A equals to mu J minus mu epsilon d squared A over dt minus the gradient of mu epsilon dv over dt. Okay. Now, Now we note that in a highly conducting material, electric field intensity E, electric field intensity E is very low. So we have seen in previous chapters also that electric field intensity inside the conducting material is zero. So in our case also the electric field intensity in our material is very low, and okay, we define this, and in order to define the electric field intensity we must do some manipulations here. Namely, we move the gradient inside and we take the derivative with respect to time outside. And what we get after this manipulation, we get the Laplacian of A equals to mu j minus. So, okay, let me first write mu epsilon d squared A over the t squared. Okay, here also square, here also squared, minus d over the t mu epsilon gradient of v. Okay, so I think it is better if I continue in this page, so that's why let me again scale down all the nodes and I put them here. Okay, now we take mu epsilon and one of the derivatives out of the brackets, and we have minus Laplacian of A equals to mu j of minus plus mu epsilon of the t, and inside the bracket there remains minus dA over the t minus the gradient of v. So from the previous notes we know that this is equal to electric field E, and we said that electric field E inside the conductors is very 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 low, and we can write is approximately equal to 0, and remains only this part of our equation. It's part of our equation, and if we write it here, what we get, the Laplacian of A will be equal to minus mu j. So we derive this equation. Okay. Now, the next comes the interface conditions. Okay, interface conditions is boundary conditions. Okay, in this book it is called as interface conditions. Let's discuss the interface or boundary conditions in electromagnetics. So far we have discussed the boundary conditions in electric fields or in magnetic fields. And what are the boundary conditions in time-dependent fields? So far we discussed only stationary fields. Okay. Sorry, this is not the case that I wanted to copy. Okay. This is the table which shows the summary of the electromagnetic field equations and interface conditions. Interface conditions is equivalent with boundary conditions. Just please don't be confused. Okay, we have already learned boundary conditions for electric uh, for electric fields was equal to this, and for magnetic fields it was equal to this, and the same boundary conditions in dielectrics were these equations. And what are the interface or boundary conditions for time-dependent fields? In the case of magnetic fields, you may see no, sorry, in the case of dielectrics, you may see mm, nothing changes in boundary conditions. What about in the case of time-dependent electric field and time-dependent magnetic field? Time-dependent electric field and time-dependent magnetic field. So, there are several rules how to derive the uh, boundary conditions. So, first of all, two general materials are assumed to be in contact, forming an interface. By an interface, we mean an infinitely thin boundary with no properties of its own. On each side of the interface, the materials have uniform properties and are linear. The interface may contain surface current densities and surface charge densities. This is the first rule. Second, Maxwell's equations in integral form are applied to the interface. From this, we find the conditions on the electric and magnetic fields on both sides of the interface, since the fields must satisfy Maxwell's equations everywhere. Next, third, conditions at the interface are given in terms of components of the field at the interface. The tangential and normal components at the interface are the required interface conditions. And the last two is the interface conditions for the tangential components of electric field intensity E is derived from equation 1128, which is so 1128, this equation. This equation is used to derive the interface conditions for tangential components of electric field intensity E. And 1129 is used to derive the interface conditions for tangential components of H, which is magnetic field intensity. Okay, now let's try to derive the interface conditions for the electric field. Well, let me copy the drawing. So first, to derive the interface conditions, we assume two different materials with properties as shown in figure A. Two different materials. Okay, you may assume that this side is first material and another side is the another material with different properties, with the properties which are epsilon 1 mu 1 and epsilon 2 mu 2, and we assume a surface charge density rho. This is surface charge density rho s at the interface between the two different materials, and apply the equation that we showed a moment before, where we showed this equation here. Okay, I will write one more time this equation. Okay, let's write the equation 1128. So integral over the closed path. In this case, closed path is from A to B C, D, and A. So closed path is A, B, C, D, A of E dl equals to minus the change of uh, magnetic flux in the surface of a BCD A over time is equal to 0. So we can note the following. The total flux phi. So first of all, let me again scale down this. Okay, I scaled down, and for now we don't need this part of our figure. And okay, first of all, we know that total flux enclosed in the loop A, B, C, D, A is equals to 0 because in the limit the area enclosed by the loop is 0 because that this area, when the length of a not AD DA length of DA goes to 0, this surface S will also go to 0. That's why flux will also go to 0. Okay. That's why total flux enclosed in the surface ABCDA is 0. So the distance BC and DA also tend to 0. Okay, we have said this already. Distance BC and DA also tends to 0. The electric field in material 2 is in the direction of integration, the direction of dl. Okay. In material 1, the electric field intensity is in the direction of opposite to the direction of integration. Okay, and here electric field, so or we may look it at electric field. This is in general in the direction of integration. The direction of integration is this, and our electric field E1 is opposite from the direction of integration. This is the direction of our electric field intensity, and this is the direction of integration. So, and from these considerations, we can write that. Okay, we can write this integral in the form of integral of closed path A, B, C, D, A of electric field intensity E dl equal to integral over the path AB electric field to 1 dl plus integral over the path CD of electric field 2 dl, which is equal to 0. Okay, which is equal to 0. It goes from this. And since the tangential component of E2 is in the direction of dl2, okay, this is the tangential component of E2. Okay, this is the tangential component of E2, and this is the direction of dl. They coincide with direction, and tangential component of E1 is opposite from the dl1. Okay, here don't forget, here dl1, dl2. So what we have now, let me split this in order not to be confused. What we have now, we have minus E E1 T dl1 equals to, from A to B, from C to D, no, okay, from A to B, plus from C to D, E second tangential component of second electric field intensity by dl2, which is 0. Okay, now and so the distance AB and CD are equal. So as the distance AB and CD are equal, we have, okay, from this integral we have the tangential components of E1T equal to tangential component of E2T, or in case of dielectrics, d1t over epsilon will be equal to d, okay, epsilon 1 d2 t over epsilon 2. So these are the boundary conditions or interface conditions for time-dependent electric fields. So from this two equations. Following conclusions can be drawn. The tangential component of the electric field intensity is continuous across the interface between two general materials, regardless of charge densities on the surface. So the tangential components of electric field intensities are continuous. They don't they don't interrupt, or they don't jump in the interface. The tangential component of the electric flux density, which is D, electric flux density, is discontinuous across the interface, or electric flux density D, the tangential component of electric flux density D is discontinuous in the boundary conditions in the boundary of two materials. The discontinuity is equal to the ratio between the permittivities of materials. Yeah, the discontinuity is equal to ratio epsilon 1 over epsilon 2. Discontinuity is equal to this ratio. Interface conditions or boundary conditions for the electric field intensity are independent of the magnetic field. So boundary conditions of electric field intensities, these are independent of magnetic field. Okay. The interface conditions for the time-dependent electric field are identical to those for the static electric field. This is the consequence of Faraday's law. Okay, as we can see here, and also we derived in previous classes, we derived the boundary conditions for static electric fields, and if we remember, both boundary conditions are the same. In both cases, the electric tangential components of electric field intensities are continuous on the boundary or on the interface. Okay, now let's derive the interface conditions for magnetic fields. Okay. Now we need the second picture. We need this picture now. Okay. So we have the two different materials with common interface or with common boundary. We use the following considerations. The contour ABCDA encloses the interface alone. That is, BC and DA tends to 0, and the area of the contour tends to 0. Okay, the considerations are the same as before. So if we consider path ABCDA, that BC and DA tends to 0, that's why S also tends to 0. Surface also tends to 0. The tangential component of the magnetic field intensity in material is in the same direction. So in material 1, this is the medium 1 or material 1, and that is in this side the medium 2 or material 2. So as we can see from the picture, the direction of integration is this, and tangential component of magnetic field intensity is this. For the material 1, the directions coincide with each other. For material 2, directions are opposite. The total current and the last consideration is the last condition or consideration assumption. The total current enclosed by the contour is equal to the current density on the surface multiplied by the length AB. Okay, the total current for the total current we use the current density on the surface multiplied by the length of AB or CD. Okay, and now, sorry. Now, from all these conditions, we can write that integral over the closed path ABCDA of magnetic field intensity DHDL equals to. So we don't take into account the path BC and DA because they tend to 0 and remains only integral over the path AB in the first, so in the first material, that's why H1 of tangential component DL1 minus, because in the second case the direction of tangential component is opposite from the direction of integration, CD of H to T DL2, and all this equals to the integral over the AB of J S DL. Okay. Equal to integral JS DL. Okay. Now, let's look at equation 1129 here. Let me copy this and paste it somewhere here. This equation will be useful to us. If we look at the equation 1129, the integration for current is a surface integration because, well, yeah, you may see here surface integration because in general J is a current distributed over the volume. Okay, however, here the current is distributed over the surface, therefore integration is on the line AB. Here our current is distributed on the surface, that's why we take the integration on the line AB or CD. And the area enclosed by ABCDA tends to 0, and therefore surface integral over the volume current density, which is this, also tends to 0. Okay, recording. Okay. So we said volume current density also tends to 0, and choosing that AB equal to CD, we have all from this, we have H1 tangential minus H2 tangential equals to JS. And B1 tangential over mu1 minus B2 tangential over mu2 equals to, again, JS. Okay, and so these two boundary conditions for magnetic fields can be summarized as follows: that tangential component of magnetic field intensity, which are H1T and H2T, are discontinuous in the presence of surface current densities. It means if surface current density is not 0, in that case tangential component of magnetic field intensity is discontinuous in the boundary. And also the tangential component of magnetic flux density, which is B1T and B2T, is also discontinuous. Okay. So what is next? Okay, next comes the tables that summarize the interface conditions and several examples. Okay, we will do that examples in the next lesson. Now I want to add one more thing. Please be patient. Okay. So normal components of h1 minus h2 is equal js, or okay, or similarly normal components of b1 over mu1 minus b2 over mu2 also equals to js. These boundary conditions can also be used. Okay, thank you for your time. In the next lesson, we will try to solve some problems, and we continue next time.